Heaven high poop push. Heaven high poop push.
Hello people. Hello people. Seriously, how did none of you notice that? Let me guess. You were too distracted by the floaters drifting in front of your eyes. You know what? It's okay. It happens to me too. So yeah, I'm Carrie Kitten Hugger, and after a 5-month hiatus, 6-month hiatus,
8-month hiatus,
11-month hiatus, I'm back. No way, it's 2018 now? Anyway, do you ever just want to go out to the city and watch some really cool dance performances? But then you see— oh my god, what the frick, Carrie? What the hell do you think you're doing? Please stop. As you can see, the premise is that humans suck at dancing. Well, at least some humans— Shut up! Can we program an AI that dances any better? Well, probably not with current technology, but regardless, let's give it our best shot. Michael and James have both convinced me to keep this short, so I'll try to. First, we need to define what a dance is. Put another way, we should concretely define what file type our AI should output. A text file of dance moves? Perhaps a list of all the angles of each joint over time? We're actually not going to do either of those. Why? Because they're boring. Instead, let's try to generate full-on dance videos. That might sound daunting, but let's remember that a video is really just a sequence of images played at a certain frame rate. So, if we can simply create an AI that can observe a sequence of thousands of images, learn from those observations, and then output its own sequence of images that mimics the patterns of the originals, then we're good to go. To produce such an AI, it might actually be easier to modify somebody else's code that's already been proven to work. Okay, this may be the 500th time I've mentioned Andre Karpathy's text-generating recurrent neural network, but that's because it's just so darn useful. You provide it some text dataset to look at, like all of Shakespeare's works. If it trains on that dataset successfully, then it can generate output that resembles the patterns of the training data as close as possible without copying the text verbatim. So you get this fascinating pseudo-Shakespeare. Now, this neural net has already been online for anybody to use for about 2.5 years. My job is to modify it to produce images instead of characters of text. How do I do that? Well, looking closely at Karpathy's code, we can see that each text character is actually represented as a list of numbers, where each number answers the question, is this character an A? Is this character a B? Is this character a C? And so on. To clarify, 0 means no and 1 means yes. That means if there are 95 types of characters, then we have to answer 95 of these questions, so there's a 95-dimensional vector corresponding to each character. This is called a one-hot encoding, and you might think it's vastly less efficient than, say, plain old ASCII encoding, but it actually works better. Read this if you're curious. Moving on, if the meat of the RNN only plays around with these one-hot vectors, then, in theory, we could just replace the input and output to any other set of vectors, and the RNN should be just as effective, right? Well, that's what I was thinking. Here's some boring details. Now, the question becomes, how can we convert each frame of our dancing video into a vector that can then be fed into the RNN for training? That seems a little tough. To figure that out, it might be a good time to actually collect the dance videos we'll use for training. So let's do that, using the internet. Fancy dance videos like this look really cool, but to be honest, our RNN here has limited power, and if we feed it data that's just too overloaded, it will scream in agony. Do you hear it screaming? I sure do. We'd rather just produce a baseline dance generating AI that proves that the concept works, so let's go as bare bones as possible. How about a purely black and white dancing silhouette? Okay. Alright, so my goal is to scour YouTube and find a sufficiently long video of dancing silhouettes. Now, they don't have to be pitch black and pitch white right now, because I can process and edit the videos later, but the closer to that we can get, the easier it'll be for me. So I'll just search dancing silhouette, and that's it. Let's see what I get. Aha! I managed to find a 1.5-hour video of black silhouettes of women dancing to techno music in front of colored backgrounds, uploaded by Haluk Arslan. This video is only from the hips up, which is not quite what I wanted, but again, proof of concept. Remember, we defined a video as a sequence of images, right? So we need to turn Arslan's video into a sequence of images. I use Sony Vegas to save every 3 frames of this video as an image. This speeds up the dance 3 times, but hey, they were too slow to start with. And downscaled them from 1920 by 1080 to 96 by 54. Using processing, I'll turn any pixel that isn't pure black into pure white. Voila! We now have this bundle of 18,000 sanitized images in sequence so that our AI can use them. Oh wait, it's not fully sanitized? There are parts where the background removal didn't work that well? Psh, I don't care. If less than 5% of the dataset is dirty, then our AI will just have to grin and bear it, and I'm sure it'll be fine. To clarify, all these steps are done just to lighten the load on our poor little RNN. Since we still have enough information to see what dance pose is being made, we can still see whether the RNN was successful or not. So let's get to work integrating this old AI architecture with this new dataset. Each image is 96 by 54 pixels, with each pixel being a brightness on a scale from 0 to 1. That means if each pixel corresponds to 1 dimension, this image can be represented with, yikes, a 5,184 dimensional vector. That's a lot more than the 95 dimensions our poor little RNN is used to. Can you at least give it a shot, RNN? Okay, we can stop. I guess 5,000 is just too much. That's fine. Somehow, we've got to communicate the gist of each 54p image with less space than 5,000 dimensions. Essentially, we want to compress it to a smaller file size so our RNN can handle it. Compression? Are we talking about like the compression algorithm JPEG uses? Not really. JPEG works really well on all types of images, but our compression algorithm can actually compress much further if we specialize it on just our dataset. But why is it the case that the more specialized an image set is, the smaller we can compress them? Think about the extremes. If our dataset was just identical smiley faces and frowny faces, we could encode each image as a 0 or 1, and a user who knows our compression algorithm could reconstruct those images perfectly. You might be thinking that we have to store the descriptions of the 2 images somewhere, and yeah, we do, but that goes in the compression algorithm, which is separate from the image files themselves. This means the file size of each image is 1 bit. That's a 1,000,000-fold compression, much better than a JPEG could do. But in reality, our dataset isn't just smiley faces and frowny faces, it's thousands of dance poses. So our compression algorithm will have to be much more complicated. Fortunately, we don't have to write it ourselves. We can train an autoencoder to learn such a compression algorithm on its own. What's an autoencoder? I'll explain in another video. But put simply, it's an hourglass-shaped neural network that takes an input image, encodes everything relevant about that image into a tighter space in the middle, and then reconstructs the original image as close as possible on the output side. If you want to learn more about how the autoencoder is actually doing the converting, watch my video about convolutional neural networks, hint hint, wink wink, nudge nudge, stab stab. You can think of the tight encoding as a different file type, like bitmap turning into JPEG. But in our case, our file types are typical image, 5,184 dimensions, and a single small layer of neurons that could either be more activated or less activated, 128 dimensions. Each dimension hopefully describes a meaningful attribute about the image, like how high the right arm is raised. So in this demonstration, we can use 10 sliders to fully define the dance pose of the stick figure on the right. That means we could, theoretically, encode any picture of the stick figure into a 10-dimensional vector. But no real-life autoencoder is as ideal as this one. Also, do you like my dancing stick figure tool? I made it just for you! If we separate the 2 halves of the autoencoder, we have an encoder and a decoder. The encoder will convert any standard image from our dataset into its corresponding 128D vector, which we'll call its dense representation, because it takes less space. The decoder will convert the dense representation back into its corresponding image. Seems good in theory, but does this all work? Well, it actually does. Surprisingly simple autoencoders have been proven to work surprisingly well on handwritten digits. This has a few applications, including denoising images. So let's tweak the code a little bit to run on our dataset of dance poses and then run the code. Right now, I'm showing a random image from the actual true dataset on the top. The autoencoder is going to try to encode it, reconstruct it, and give us the exact same image on the bottom. Okay, that wasn't even close. But that's because we haven't trained it on our dataset yet, so how could it even know what attributes to encode? Let's see it train. And remember, the goal is to have the output image replicate the input image as close as possible. Ideally, there'd be no difference, and converting from an image into a dense representation and then back into an image would look identical. Okay, although it's taking its sweet time, it's pretty clear that the autoencoder is indeed improving. So if we just let it run for longer, it'll get really good. Although, I'm gonna be honest, the reconstructed image always looks a little blurrier than the original, even after a full night of training on my computer. By the way, here's a batch of 10 images, their dense representations, and their reconstructions. As you can see, we humans can't make sense of the dense representation at all, because it's honestly just a slew of numbers. But at least we can tell that similar images nearby in pixel space correspond to similar vectors nearby in vector space. Side tangent, if you want to see a fascinating way to make sense of dense representations of images, check out Kevin's video, where he uses principal component analysis to find the 80 most important dimensions among high school yearbook photos, ordered from most important to least important. It turns out, the 10 most important dimensions are all fairly intuitive for humans, which is actually pretty astounding. But yeah, I didn't do that for my project. To summarize, now, our file converting autoencoder works. So that means we have a working AI that generates dances, right? Hooray! No, not true. Remember, we have two neural networks. The autoencoder we just trained doesn't actually dance, it merely serves as a file compressor. It shrinks files so that the RNN, our true dancer, can handle them. And we haven't trained our poor little RNN at all yet. So RNN, come back here! I know I made you scream in agony twice, but you know what they say, third time's the charm. Now, remember how our original dataset is a sequence of 18,000 images? Well, now that we have a file converter, let's run each image through that file converter individually. This gives us a sequence of 18,128D vectors. We said that our RNN is used to 95D vectors, so 128 actually isn't too far from that. Based on what I've seen so far and just a bunch of naive optimism, it seems like this sequence of 128D vectors that represents a dance is perfect for our RNN to train on. If it can train successfully, then it can generate brand new sequences of 128D vectors on its own. So RNN, it's time to start training. And you're done. Well, in that case, it's time for the RNN to generate a vector string. Let's set the length to 100. As I've previously stated, we humans won't be able to make sense of this slew of new vectors, but we've got a file converter. Decoder, I want you to convert those vectors back into images. Okay, now we have 100 AI-generated images of a dance. Literally, all we have to do now is stitch them into a video using some video editing software like Vegas Pro. And then we'll have a brand spanking new dance that's the bomb. I mean, looks like the remains of a dancer who got hit by a bomb? Oh, seriously? All that hard work for a blurry, ghosty smear thingy? If I want to be technical, actually I don't, because it would take too long to say. God, why does everything I write end up so long? But in short, the reason why I think this happened is that the middle of the road is always the safest option to guess. So because our RNN wasn't super confident, it gets the average of all dance poses, which looks like a blur. So anyway, let's just see what happens as I give the RNN more and more neurons. Okay, so we have a clearly defined figure now, but it's frozen with stage fright. I mean, who can blame them? They're being watched by how many people right now? Ooh, yeah, that would have freaked me out as a 1-month-old baby too. You know what, dancer? It's okay. Just pretend all the people out there are only wearing underwear. Wait, you are? Freaking disgusting! Is that motion? Oh my god, finally! It worked! Seriously? Dancer? Seriously? Snap out of it! Punching over and over again is not dancing. What's that? Okay, yes, I'll admit, my middle school dances were all just jumping up and down. But you're better than that, so let's see something better than that. Okay, good. Are you kidding me? Okay, fine. I'll give you an even bigger brain. Hey guys, Carrie here. I'm going into ramble mode because this is the final stage of my project. Meaning, like, after giving the neural network 3 layers and something like 5 million neuron connections, and training it for 18 hours, I was finally able to get this final version of the dancer. I said final too many times. And to be honest, I'm really happy with it, because you can see a clearly defined human figure making dance motions, and it doesn't get stuck in loops like the last one. However, I do realize the danger of overfitting. Considering I only trained the RNN on 18,000 training examples, and there are several hundred times more neuron connections than that, it's almost guaranteed that the RNN could just memorize the dataset and replicate it verbatim. Which is sad, because that means the video that AI produced right here might just be a copy of the original video, but blurrier and low resolution. But even if that is the case, I'm not too sad about how this turned out. Why? 3 reasons. 1. The easiest way to combat overfitting is just to get more data. And I know I can call up Extreme or Common Origins people to film themselves dancing. Plus, I could actually get them to film their legs, so we can finally see a dance of the full body. Additionally, the dance moves in Arslan's video were pretty basic, which isn't a problem, but it would be interesting to see how well the RNN could do if I fed it more advanced dance moves, like the splits, or air flares, or arms bending backwards, I don't know. The second reason I'm not too sad about this project is that the AI can generate dancing silhouettes endlessly, meaning I could get my computer to dance for 100 days straight at almost no cost if I wanted to. No human on Earth could achieve such a feat. What's the third reason I'm not sad? Well, it turns out that this whole project was actually for a computer science class at Stanford. Specifically, it was CS 221, Artificial Intelligence Principles and Techniques. It was taught by Percy Liang, so major shout out to him for leading such a fascinating class. I did this project with my friends Cindy and Connie, and when we submitted the project proposal to the teacher's aides, they told us this would be too hard to complete in 6 weeks. Like, if any step of the process couldn't be finished, we'd be left with nothing to show at the final poster presentation. So, for us to get a result that shows a dancer moving at a reasonable pace, making somewhat reasonable moves at all, I think is a triumph. Also, yes, I took the class in fall of 2017, which means this video is literally 7 months behind, but hey, I got to it eventually. Which brings me to my next point, which is that I'm taking way too long to make these videos. I've honestly missed interacting with the YouTube sphere over the last 11 months, and it feels great to be back. If you've wondered where I've been for this last year and want to stay more up to date, you can always check out my vlogging channel called Humany, although I'd hesitate to even call it vlogging because it has the most garbage content ever. But since my last good Carrie KH upload in 2017, I've uploaded 104 videos to Humany, which gives you a sense of my upload frequency there. But now we should bring the focus back to Carrie KH. Considering everything realistically, my workflow just isn't sustainable. So I've considered a few ways to resolve this, like bite-sized 5-minute videos, AI-generated lip sync, and maybe even hiring a handful of animators. Nothing's finalized yet though, and I'll let you guys know when some change to my workflow happens. Finally, let me end this video by saying thank you for watching through such a long, silly video about a whimsical school project that may not have actually produced any meaningful results. You made it to the end. Honestly, knowing that I could turn this inconsequential school project into something that I could share with this wonderful community on the internet is actually what motivated me to try hard on it and not give up until I saw good results. Otherwise, we might have picked a project that was more boring and easier, like producing music, lol. So thank you for giving me something worth fighting for. Throwback Thursday, I remembered I showed you guys the exact moment I hit 100,000 last March, and well, I'm at 279k now, so here's footage from last September of me hitting 200k.
9s always look like they're smiling because the bottom part is curved where the mouth would be, and the top is like the head. 6s, they don't look like heads, so I wouldn't say they're frowning, but 9s are definitely smiling. Okay. One more subscriber to go. It's better. It should happen in the next 5 minutes or else. Oh, there we go. 200,000. Yes. Carrie Cage, 200,000 subscribers.
See you all next time.